Hello everyone, myself Ashish Desai, Assistant Professor, Mechanical Department. Today we are going to discuss here the unit number second, fluid static. So in that content we are going to discuss the buoyancy and flotation. So first of all we look at the learning objective for this session. So first learning objective is to know the buoyancy and flotation. Second learning objective is to know about the Archimedes principle. So after this session, some learning outcome is there. The student will able to explain buoyancy and flotation. So this is learning outcome first. Second learning outcome is the student will able to explain about the Archimedes principle. So in last lecture we have discussed regarding the hydrostatic forces which is on submerged bodies for inclined surface, then curved surface, and horizontal and vertical surfaces. So first of all, in that content, we have discussed the buoyancy. So whenever a body is immersed, which is wholly or partially, which can subjected to upward force, and which is opposite to the action of gravity, that is called as buoyancy. And the force tending to lift this such conditions that known as a buoyancy force, or can say buoyant force. So this is regarding the buoyancy. So again, I repeat this concept. Whenever a body is the dipped into the fluid, which is partially or wholly, and it is subjected to that upward force, which is opposite to the gravity, that is called as buoyancy. And this force can be tending to the lifted up the body in such conditions, that is called as buoyant force, or can say buoyancy force. So this is regarding the buoyancy. Now we go for the principle, that is Archimedes principle. So simple principle is there. When you placing object, or can say lower the object into the container, so the object displaces the water which is flows into the smaller container. So whenever the placing of the object is there, so that time the water will be flows from this bigger container to smaller container. And when the object is completely submerged, then the volume of the displaced water, which is equal to the volume of this object. So this is the principle of Archimedes. So here it states that the body is partially or fully dipped into the water at rest. This fluid exerts a upward force of a buoyancy, which is equal to that weight of the displaced fluid. And if the force of buoyancy equals to weight of the solid, then that called as a flotation, or can say that equilibrium condition, that force is called as flotation. So whenever these two condition is satisfied, that is force of buoyancy which is equal to weight of the body, then this equilibrium condition is called as flotation. So this is regarding the Archimedes principle. Now we move for the causes of buoyant force. So buoyant force is the increasing of force on an object exerted by a surrounding fluid. So when object is pushes the water pushes back much as possible, so that can helps to the object can float. And if it is not, it floats, or can say if it not push the water, that part will be sinks. So example is steel. So steel is at the tip because it not pushes the water, which is hardly. So but in case of the ship, it can more water can suck and uh, pushes back to the hard, that is called as, that's why it is called as uh, balancing of buoyant force and weight. That's why it is nothing but a flotation. Now next concept, that is the center of buoyancy. So where the force of buoyancy is acted, that point is called as center of buoyancy. So here the definition is the point through which the force of buoyancy is supposed to act is known as center of buoyancy. So here the point B is there. So that point B is called as buoyancy, where the buoyancy force is acted. Okay. So this is called as center of buoyancy. Now we move for the examples. So here the wooden block is there. So that wooden block is placed here, and which is width 1.25. Width is 1.25 meter and depth is 0.75. So depth is 0.75 and length is 3 meter. So here length is 3 meter, that is length it is not mentioning, but that length is 3 meter. So this is cross sectional area we can place here. So length is 3 meter and is floating in a water. So it is floated in a water. Specific weight of wood. So specific weight of wood is 6.4 kilonewton per meter cube. Find the volume of water displaced. So find volume of water displaced and position of center of buoyancy. So here two terms is required for the problem, that is volume of water displaced. So how much water it can displaced, as well as the position of center of buoyancy, that is h bar we required over here. Now we go for first given data. So as we know that width is 1.25, depth is 0.75 meter, length of this wooden block is 3 meter. So first of all we calculate this the volume of block. So for the finding of volume of block we can multiply this 1.25 into 0.75 into this 3. So that gives the volume of the block, that is 2.812 meter cube. Now we know that the specific weight of the wood is 6.4 kilonewton per meter cube. So this is the specific weight. So first of all we convert into Newton per meter cube. So first of all we multiply this 1000. So that converts into 6.4 into 1000 Newton per meter cube. So as we know that the specific weight, so specific weight is one formula is there, that is weight upon volume, correct? So if you require this weight, what will find out, weight of the block is equal to specific weight into volume. But now one another formula for specific weight is there, that is W is equal to rho into G, right? So here I mentioned W is equal to rho into G. So here I can place the rho into G. This is the specific weight. So I placed over here, that is why the equation becomes rho into G into volume, right? So now we know that the volume is known to you, correct? Then this that specific weight, that is rho g is already know, that is specific weight, that is 6.4 into 1000 we can place here. Volume is already known, that is 2.812, we can place this, and then we have to find out the weight of the block. So this is weight of the block, 18 into 1000 Newton. So this is regarding the weight of the block. So here I clearly mentioned that the first of all we mention this the volume, so length with height, so that gives volume, correct? Now we go for the specific weight of the wood. So specific weight of the wood is known to you, but it convert first 6.4 into 1000, that is Newton per meter cube, like this. Then we go for the formula for specific weight, that is weight upon volume. So what is the weight? Weight is equal to specific weight into volume. So here specific weight into volume. So specific weight is mentioned here, that is 6.4 1000 into 1000 and into volume. Volume is 2.812. So like this we can formulate, or you can say directly you can put the value of rho g also here. So otherwise you can directly put the value 6.4 into 1000 like this, into volume is 2.112. Now we can formulate the relation and then get the equation for weight of the block. So this is the 18 into 1000 Newton. So this is weight of the block we can calculate it. Now we go for volume of water displaced. So first of all we know that the weight of the block, that is 18 into 1000. Now we know that volume of water displaced. Volume of water displaced is equal to weight of water displaced divided by weight of density of water. So volume of water displaced. So how to find out this? Actually weight of water. So weight of water is nothing but the weight of the block, because block weight and water displaced is same. But the weight of density of water is 1000 into 9.81, because weight density is nothing but rho into G. So here unit is Newton per meter cube and here unit is Newton. So Newton get cancelled and unit is meter cube. So that's why we get the value of volume of water displaced like this. So here we can place the weight of block, which is in terms of Newton, 18 into 1000, and weight density is 1000 into 9.1, that is Newton per meter cube. And if you solve it, that is square, we can get in terms of meter cube. This is regarding the volume of water displaced. Now we go for the position of center of buoyancy. So that is nothing but h we have to require here. So first of all, we require the that volume of equilibrium condition you can put here. So volume of wooden block in water. So wooden block is in water, that is nothing but small h is present. So that h at 1.25 and width is 3. So that's why I can write equation for the wooden block is, because wooden block is in water, that's why h is the height. So I can write h 1.25 is for width and that length is regarding 3, and which is equal to volume of water displaced, because we have to conditioning is a equilibrium, because it is the Archimedes principle, because Archimedes principle state that whenever the volume of the block is there, so that equals to volume of water displaced. So this is simple principle. So here we can equate these equations. Okay, volume of water displaced is 1.835 already calculated here, and then find out the value of h. So this is called as the position of center of buoyancy. So this is position of center of buoyancy. Okay, so here we can get the position of center of buoyancy, and here from the base center of buoyancy is, so that center of buoyancy h is your this height, but for the buoyancy point we can divide by 2. So that's why we can becomes 0.244 from the base. Now next example is, this is a metallic cube 30 centimeter side and weighing is 450 Newton, is lowered into tank containing a two fluids. So here the tank is placed and there are two liquids. So first liquid is water and mercury. So first liquid is water and mercury. Because of the density factor, the mercury is at the bottom and water is upper side, because density of mercury is higher than water. So that's why mercury is at the bottom and water is at the upper side. Now determine the position of the block at a mercury water interface when it is reached at a equilibrium. Now we go for the metallic tube, which is in a come into the water surface and come into the rest of the mercury. So first of all, we know that the flotation principle, that is weight of the cubical block is equal to Buoyant force. That weight of the block is equal to Buoyant force. So first of all, we know that the weight of water and mercury displaced by the block. So this is regarding the Buoyant force, because that can be displaced the weight of water and mercury. We are putting the block. Now we go for the weight. So weight of the cube. How to calculate the weight of the cube? That is nothing but specific weight. Actually, specific weight is nothing but weight upon volume. So for finding out weight of the cube, that is equal to specific weight into volume. Now we know that the cubical block, that is weight of the cubical block is 450. So already mentioned that 450 Newton. Weight of the block is 450 Newton, and weight of the water, so weight of the water plus weight of the mercury, because this is a lie between 2 points. So for weight of water, first of all weight of water, so we can place the specific weight into volume. So specific weight is that is nothing but rho into g. So for water purpose, rho is 1000, g is 9.1, and volume for water, so water is up to this interface, that is nothing but h1, then this is the zero point 0.3 and this is 0.3. Why it is 0.3? Because convert into 30 centimeter to 0.3 meter. So 0.3 meter, 0.3 meter and h1. So here I write h1 into 0.3 into 0.3. So this is for water purpose, plus for mercury purpose what will happen, 13.6 into 1000, because this is conversion of that specific gravity to density. That's why 13.6 into 1000 into g, that is g 9.81 into into what? It is for water mercury purpose. That's why H2 zero point 0.3 into 0.3 into 0.3. So after that equation becomes H1 plus H2, right? H1 plus 13.6 H2 is equal to 0.509 meter. Equation number 1. And for equation number 2, what will happen from this figure? H1 plus H2 is equal to 30 centimeters. So I can write 0.3 meter. Okay, like this. Okay, so this is the equation number 2. So after equation 1 and 2, we can solve it and we formalizing for this H1 and H2 values. So after that, we can get the value of H2. So this H2 is equal to that the interface of the points, the position of interface. So position of interface means this point is required over here, and after this solution, we get the value of H2. This is about 0.01658 meter. Now we go for the next problem, that is stone weighs. Stone weighs 392.4 Newton in air. So per the and 196 point Newton in water. So here one container is there. Half portion of the stone is at the air and half of the portion is at the water. So here we can compute the volume of stone and its specific gravity. So first of all, we know that the weight of stone, that is 300 Newton, that is 92.4 Newton. Weight of the stone in air and water, so water is there 196.2 Newton. Now we know that the for equilibrium condition, so here equilibrium condition is there, so weight in air, so weight in air minus weight of stone in water, so we can minus it, so that will gives the weight of water displaced. Correct, because this is from flotation principle. So whenever the buoyant force and that solid force, I can say solid of that block, which will be equal, or you can say equilibrium conditions, so at that time it is called as flotation. So here weight in air minus weight in stone, we can minus it, then we get the value of weight of water displaced. So weight of water displaced. So calculate this. So weight in air is already known to you. Weight of stone already known to you, that is 196.02 is equal to weight of water. So weight of water means rho into G. Rho is the 1000, G is 9.81 into volume, because specific weight is equal to that into volume, right? Specific weight is equal to weight upon volume. Weight is nothing but specific weight into volume. That's why 1000 into 9.81 into volume. Correct? So that's why that equation becomes the formulation regarding this, the volume of water displaced divided by this value. So it will get the 202 into 10 raised to 4 centimeter cube. So this is regarding the volume of stone. So when you call that the volume of water displaced, so that is called as volume of stone. Correct? So this is the regarding the Archimedes principle. So whenever the volume of stone is placed in water, so that can displace some water. So that's why I can equate these two equations. Now that's why I can write as a volume of stone is 2 into 10 raised to 4 centimeter cube. Now we go for the next point, that is specific gravity. So specific gravity, for that purpose we require the mass and density. So if you require the mass, that is nothing but W is equal to mass into gravity. So weight divided by G, that is nothing but mass. So mass is equal to weight upon G. So we can put the weight from in the air, that is 392.4, G is 9.1 is equal to 40 kg. So after that we can plot the mass in air divided by volume, that is 40 kg. Volume is already calculated from the figure, that is 1 by 50, and after that solution we can get the density of stone. Now we can calculate for the specific gravity of stone, that is density of stone divided by density of water, that is nothing but 2000 divided by 1000 is equal to 2, that is the specific gravity of stone, that is nothing but the specific gravity. So actually specific gravity is nothing but density of stone divided by density of water. We can place density of water is constant, that is 1000, and for stone purpose we calculated here, that is 2000. So this is regarding the specific gravity of stone. Now we move for the next problem. So here the body is having dimensions, that is 1.5, 1 into 2, that is the volume, and which weighs 1962 Newton in water. Find its weight in air. What should be its specific gravity? So first of all, we go know that the volume of the body, that is 1.5 into 1 into 2, that is nothing but 3 meter cubed. And for weight of the body, that is 1962 Newton, that is given data. So as you know that volume of water displaced is equal to volume of the body. So volume of the body is 3. That's why volume of water displaced is 3. Correct? Now we have to require the weight of water displaced. So as you know that weight is nothing but specific weight is equal to weight upon volume. So what is weight is equal to specific weight into volume. Specific weight means rho into g. Rho is water, that's why 1000, g 9.81 into what? This is the volume. So that's why you can take 3, and that's 3 from this volume of body, right? And after this calculation we get the 29,430 Newton. So this is about weight of the water, right? Now we move for the equilibrium condition, that is the for body. So here weight of the water body in air, weight of the water displaced is equal to weight in water. Okay, so now we put the value of their weight in air minus 29,430, that is water displaced here, and weight in water, that is 1962. So after that we can get the weight air. Now weight in air you can got this by equilibrium conditions, that is nothing but by floating condition. Now we go for the density. So how to calculate density? Mass of the body is equal to weight in air divided by g. Weight in air. Weight in air is how much? 31392. G 9.81, that is 32. That is 3200. That is 3200, or you can say 3200 kg. Correct. Now we go for density of body, that is mass is known to you, volume. So volume is about the block is 3, right? And mass is called 3200, that is you can get 3200, and after the solution we can get 1066.67, and after that we can go for specific gravity, because if you know the density of body, then you can take the reference for that density of water. So we can take the ratio of this, and we get the value of 1.067. So this is regarding the buoyancy and the Archimedes principle. Thank you.